Okay, students, now we'll define what is critical pressure ratio. So the critical pressure ratio is defined as the pressure ratio at which the area is the cross-sectional area is minimum and the discharge is maximum. So at which pressure ratio gives the maximum discharge through the minimum cross-sectional area. So this is known as the critical pressure ratio. And the simplified form of the critical pressure ratio, to find the critical pressure ratio, the approximations are given. So this PC by P1, so it is nothing but the end the minimum cross sectional pressure and the inlet pressure P1. PC by P1 is equal to 2 divided by n plus 1 power n divided by n minus 1. So using this relation we can calculate the pressure ratio, that is the critical pressure ratio for various n. For example, if it is air, so n will be 1.4. So if you substitute 1.4 here, so this will become a constant. So this PC by P2 will be equal to 0.528. So for air, the critical pressure ratio will be 0.528, and for the saturated steam we will put n is equal to 1.135 index value. So that gives our PC by P1 will be 0.573. And similarly for the wet steam, n will be 1.113, so that the critical pressure ratio comes 0.582. And for the superheated steam, n should be 1.3. So if you put 1.3 here and substituting values, you will get the ratio becomes 0.546. So these are the things we should know. And in the question the condition will be given, so based on the condition we have to calculate the either one of the pressure will be given, so you may be calculate the other condition. So using this we will going to solve some of the problems. So now we will try to solve one problem. So let us look at the problem given in the university. It is stated that dry saturated steam at a pressure of 8 bar so enters a convergent divergent nozzle. So it is a CD nozzle, so convergent divergent nozzle, and leaves it at a pressure of 1.5 bar. So leaves at a pressure of 1.5 bar. So if the steam flow process is isentropic, so if the steam flow process is isentropic and the corresponding expansion index is 1.135, so n value is 1.135, find the ratio of cross sectional areas at the exit and throat. So we have to find the ratio of the areas at the exit and throat for the maximum discharge. So we will get the maximum discharge only at critical pressure ratio. So this is the problem given in the university exam. So now let us try to solve this problem. So first let us understand what is given in the problem. So a dry saturated steam at a pressure of 8 bar enters. So this is the inlet pressure 8 bar. The nozzle is a convergent divergent nozzle, and it leaves at a pressure of 1.5 bar. So that is also given. So exit pressure is given, and the throat values it is not given, so we have to find the throat value. So now let us solve this problem. So here the convergent divergent nozzle will be like this. So there is a convergent portion and then a divergent portion will be there. So this is the shape of the nozzle. So this is the first point. the entry point. I am getting the minimum area, so this is the throat. So let us take throat here, so we'll put T to denote the section 10. Then the exit point, so this is the exit. The steam enters here and comes out through the exit. So this is second point. So the HS diagram for this expansion will be like this, that is, so this is the HS diagram, and here at this is the pressure 1, here it is pressure 2, and here we are getting the throat pressure PT. So these three pressures will be like this. So there are three pressure line. The pressure, the inlet pressure will be the more, so this is P1, and this is the exit pressure, this P2. So here the throat pressure will be in between these P1 and P2. So let us take this is PT pressure, and it is given that the problem is given that it is a dry saturated steam enters. So the entry point will be saturation point. So let us see the saturation curve like this. So for this pressure, so this point is the entry point. So this is our 1 point, and the expansion takes place from this one isentropically. So the expansion is isentropic expansion. The process is isentropic, it is given. So this entropy will be same for all points. So this straight line gives the expansion process. So from here the exit pressure up to this point, so this is my second point. So the pressure is reducing. So this is the expansion process from here to here. So this is first point, the entry point, which we can get the values from the steam table. This because it is a saturation point. Now this point here, the condition will be at some x with some x, that is the dryness fraction, some x, because it is in the wet region, so it should be have some xt. Similarly here this point is also, it is within this wet region, so here also you will get some x2. So here it is saturated with this dryness fraction. I am getting all the values h and s, here also this one, but the s value s1, st and s2 all are same because it is isentropic process. So s1, st, s2 all are same, some value. So that value can be taken from the steam table because the 1 point will be available in the steam tables. Okay, so now for all this point we have to take the properties. So first we will put down the given data. So what is given? So the entry pressure is given, so pressure at 8 bar, so this entry point, so 8 bar, so P1 is 8 bar, and it enters the conversion terminal, leaves at a pressure of 1.5, so it leaves at 1.5 bar. So P2 is given like 1.5 bar. Then the index of expansion is given, so n is given, so 1.135. So to find, so what should be find? The cross-sectional areas, the ratio of the cross-sectional areas at the exit. So at the exit and the throat. So this is what is the ratio. So that is the question asked. For this we'll find the mass flow rate, then only we can equate this thing to know what is this value. So the PT value is not given, so but it is given that to find the maximum discharge. So the critical pressure ratio is should be there in this point. So what is that? So solution, so this throat pressure divided by the inlet pressure is the critical pressure ratio. So what is it is given? So it is 1.135. So n index is given as 1.135. So that what I am getting is, so here we know that, so 1.135, so critical pressure is 0.573 or 0.577. So this ratio should be 0.573. Okay, so from this we can calculate what is the PT pressure. So here it is 0.573 into the P1, so inlet pressure, so it is 8 bar. So what is the value? So it is comes around 4.6 bar approximately. So here we can take this P1 as 8 bar, throat pressure 4.6 bar, and the exit pressure it is 1.5 bar. So all these three pressures are there at the different point, and we have to calculate what is the mass flow rate. So for mass flow rate we should know what is the CT value, that is the C value, the velocity. And for finding the x value, xt and x2 value, we are going to use the entropy values. So let us take the properties of steam. Okay, so properties of steam from steam table. So please refer the steam table. For first pressure, so 8 bar. So what are the values? And for the PT, that is 4.6 bar. So what are the values? And for 1.5 bar. So what are the different values for this pressure? So what are the different properties in the given table? So for mainly we need these values. For all these pressure we need what is the HF value, then what is the HFG value, then we need HG value. So all three the different point. Then we have to take what is the SF, similarly SG, and if you want you can take SFG also. And finally, so what is the specific volume at fluid side, and also the VG. For all these different pressures, we have to note all these values. For using these values we are going to substitute the values. So from steam table, for example, if we want HG value, because this entry point is saturated steam condition, dry saturated steam. So this HG value for 8 bar you have to take from the steam table. So just I will have a sample of taking the reading. So I will write the one sample. So you must write or fill the data for all other properties. So let us take the value for 8 bar. So I will take the pressure table and let us find the, so here I am getting the 8 bar. So this 8 bar pressure, so the Hg value, so here it is Hfg, it is Hg, so it is 2767.4. please note down, for 8 bar the Hg value is 2767.4. okay, so that is to be noted here. So 2767.4, so this is kilojoules per kg, the unit is kilojoules per kg. So I want this H1, so this is H value, so that is why we are taking at Hg, the first H1 point. Similarly for the other entropies, so the entropy point for this point, so that also for the same 8 bar and the Sg value. So here it is Sg value, it is given as 6.660. so for 8 bar, so 8 bar Sg value is given as 6.660. so this 6.660, so this much of kilojoules per kg Kelvin. Similarly the Vg point also we have to take. So this Vg is here for 8, and this is Vg is specific volume at 1 is 0.24026, 0.24606. Similarly you find all the values for these pressure. Okay, so after finding the values, we'll move on to get the values for the other 2 points, because we know what is the Hg value, and here Sg is S1, so that is also noted, and the Vg, the specific volume at 1, it is also noted. So now for this point we have to calculate what is the dryness fraction at X. So this entropy and this entropy are same, so I am going to use that relation here to find the values. So now what can be written like this. So for the throat point, so at the throat, the throat entropy is equal to the entropy at first point, entry point. So this throat entropy will be written like this, as we already seen in the introduction class. So this is Sf plus Xt into Sfg. So we want only this Xt. So what is the amount of Xt dryness fraction? So these other things are taken from the steam tables. So this is given, so this is equal to S1, so that is given as 6 point, so that value, that is this Sg value, this is S1, 6.660 kilojoules per kg Kelvin entropy. So Sf, you have to take it from the table, so it is 1.829, please check it. So this is 1.829 plus Xt into Sfg is from the team table 5.018. So this is equal to 6.660. So therefore Xt will be equal to 6.660 minus this 1.829, then divided by this 5.018. So it is comes around 0.9. Let's take this. So this is 6.66 minus 1.829, so divided by 5.018. So this is equal to 9.6. So this xt I am getting as 9.6. So using this xt, we have to calculate the what is the h, what is the value of throat enthalpy. So here we are going to calculate what is the h. So h1 is already known, so we have to find now the ht value. So this ht value is nothing but again it is hf plus xt into hfg, the throat pressure, at throat pressure. So everything are at throat pressure. Okay. So for this point it is the entry point. So the 8 bar values we have to take. Here it is 4.6 bar. So 4.6 bar value we have to take the hfg and hf value. So using the xt, the same xt will become here. So we have to calculate what is this one. So putting all this value from the table, I am getting, you please check, the ht value is comes around 2659.21 kilojoules per kg. So we know already what is h1, and now the throat ht is in this much. So now the volume, the specific volume at this one. So this again we can calculate from using the ht into vg at t. So at 4.6 bar, so what is the vg? You have to calculate from the steam table. So into xt 0.96, we will get the vt value. So I am getting it as, that is 0.96 into, so vgt value from steam table for 4.6 bar, so I am getting is 4.40526. So I am getting it as 0.389. So this vt, so meter cube per kg. So this is vt, so this is ht, and we know already what is h1. And now the exit condition. So now let us calculate the exit condition. So at exit, that is at 1.5 bar. So at exit condition, what is the xe? So we have to calculate. For this, I should need either the first point or the throat point. So here it is hf2, that is the second point. That is we are taking it the exit as 2. So we are denoted as 2. So that is why this h2. So this is nothing but h2. So here it is hf2 plus x2 hfg2. That is the second, this point, exit point. But we don't know what is x2. So this can be calculated again from s1, that is equal to st, that is equal to the exit value. So this exit value is nothing but sf2 plus x2 into SFG2. So this 2 what by which what I mean is all the values are for at 1.5 bar. So substituting all these values, I am getting x2. You please calculate by yourself. I have already calculated. So I am getting it. X2 is 0.9. So if you see that here the dryness fraction is 0.96. Here at x2 it is 0.9. So the dryness fraction is becoming low and low. So here it is 1. So that is saturated condition. So using this x2, putting the values here, so HF2, so HF2, that is the fluid point for 1.5 bar, and HFG also 1.5 bar, x2 0.9. So putting all this thing, I am getting it is 2476. Please you yourself calculate and find whether the answers are correct or plus or minus, with little variation can be allowed. So this is the H2 value. So this is the exist condition. So the throat velocity can be calculated as the throat velocity CT can be calculated using the formula, the relation, that is 2000. So H1 minus, here it is HT, the first thing. So here I am getting, putting the HT value and H1 value. So it is comes 468.81 meter per second. Similarly for the second, the exit point, so C2 comes like, so 2000. So here also it is H1 minus H2. So entry point value and outlet value is H2 here calculated here. So it comes around 772.19 meter per second. So we can see that the velocity is increasing. So exit velocity is some around 770 meter per second. Okay. So using these two velocity, so we can calculate the mass flow. So we know that what is mass flow. So mass flow is the area of cross section into the velocity divided by the specific volume. So here equating the mass balance, that is MT, the mass flowing through the throat, should be equal to the mass flowing outside. So what is this? So MT can be written as, say, area throat into CT, the velocity at this thing, then at 3. So specific volume at, so this is equal to at 2 point. So area 2, so into C2 divided by V2. So mass is equal, flowing is constant. So at the throat it is AT into CT divided by VT. For 2 point it is A2 C2 divided by V2. So all these things we can calculate. So CT we have already calculated, C2 is also calculated. So now only we want the exit to throat area distance. So let us take this A2 divided by AT. So this is what it is called. So now, so A2 divided by AT, then CT divided by C2 into this V2 will be go there. So V2 by this VT. So CT we know, C2 we know, and V2 we have to calculate. So it is the how to calculate V2. So this is V2 is nothing but x2 into Vg2. So this is for 1.5 bar. So you calculate what is V2 and we can get this one. So we already got what is Vt. So Vt is 0.389 meter cube. So from this also we can calculate what is Vt. So putting all these values, so I am getting this A2 by A2 by 80, that is the exist cross section to the throat cross section. It comes around 1.63 the ratio. So A2 by 80 ratio comes like 1.63. So this is the answer. So because the question is asked to find the ratio of cross sectional areas at the exit and throat. So the area of cross section at the exit is A2 and the throat is A2. So we need what is this ratio. So we have calculated this A2 by thing, A2 by 80 comes like 1.6. So this is for the maximum discharge because we are using the critical pressure ratio value initially. So that is why we are getting this ratio as for the critical pressure ratio. Okay, so we'll do in the next session the another sum for this one. Thank you.